In the previous session we discussed about the buffer overflow, and now in this session we are going to practically show a buffer overflow attack. And this is done by first disabling the security mechanisms of the Linux. I means the memory randomization process, that memory is the serially arranged rather than is randomized. We'll have to disable this, and then enabling the code dumps. This for debugging process. We'll have to set the size as unlimited. Now first let us look at the condition of the memory randomization variable. It is set to 0. If in your case it is set to 1, then you will have to set it to 0 by using these commands. Then we set the password, and then it's good to go. Here in the system.control.conf file, we are setting the variable kernel.randomized vs base 0. It means that randomization process will be stopped. Then we can check this using this command. Yes, the variable is set to 0. We can recheck whether it is globally made 0 or not by using this command. Yes, the randomized VSS variable is set to 0. Then we are good to go. Then we'll have to enable the code terms. ulimit -c unlimited. It set the size as unlimited. We can check the condition as in this command. Yes, this is set to unlimited. Now what we are going to do is we are going to write a C program, a vulnerable C program, to make a buffer overflow. Here in the main function we are seeing that it is taking arguments from the command line, and there is a buffer of the 256 characters. Now whatever string copy is doing is that it is taking the arguments from the command line and it is storing it in the character array of buffer, which is 256, and it is printing it. However, whatever the string copy does means it doesn't check whether it is 256 argument from command line is coming from of 256 characters or not. So there will be a buffer overflow by exploiting this loophole or vulnerability. Then we compile the C program. First we write the C program. Let us go to the desktop test. There is nothing there. Then first we write the C program, create a file using the touch command, example.c, then nano example.c. Here we just copy paste these things. Here it is written. Now we compile the example.c to make it executable. For this reason we'll use this command. This also using compiling the example.c to produce the output example where there will be no stack protector. That means the kernel value at the end of the buffer will be removed, and this will be done in the 32-bit structure, 32-bit program, and the execute stack is to make the stack executable. Now let us run this command. Let's run. Then we can use the debugger to see the output example, GDB example. Now we are in the debugger. We can see the assembly language instructions using the ds of the main function. This main function using the ds main command. Here we see there is lot of parameters like EBP, extended buffer pointer, extended stack pointer, and there is so on. These are all written in the assembly language instructions. Here we see that string copy at PLT. That means this line is in the this line indicates this instruction. Here if you debug and put a breakpoint and debug it, like break pointer copy this one and paste this one, that means a breakpointer will be set up at after the string copy. Now if we run a, you can see this, if we run Python to give input from the command line, run means that program will be executed, and the parameter that will pass is this the Python command using the Python, let's command line. We are just printing a 256 times. Now we are in the breakpoint. Then we can now check the memory, whatever is happening into the main memory. And for this reason we use the command x. X means the examine, and we are checking width of 200 hexadecimal. XP means hexadecimal bytes, and around the percent ESP or extended stack pointer. If we displace this, we'll see that we'll see these values. Let's just change it. We'll see the values as here we can see that all the values are stored here, and the starting point of 41, which is the hexadecimal value for A, starts from this line. So we'll have to store this. Where you can store? We just remember. We have to remember this. Copy. Let's just paste here. /x. We'll have to reverse this. For this reason, I'm just doing it because I'll explain it in before executing them. We just reverse it. And yes, we have just reversed it. I mean, we'll just keep it here. We'll come back again. Now whatever happening here is that what we want a buffer overflow attack. We can see that in the memory space, here is the buffer from 0 to 11, 256. In our case 256 will be stored. Then if we make a buffer overflow attack, then we'll have to overflow the previous frame pointer and return address. And for this reason, and the return address, we'll have to make a return address to point to such a address such that whenever it is executed, we can gain an access to the command line. And here the other instructions are stored. So whenever we point this return address and the buffers are overflowed, it will have to overflow up to this, and using the no-op operations, and at the end of no-op operations we'll have to store the whatever malicious code we want to store, so that when the return address finds the no-op operations, it will just continue to the next operation, no-op operation means performing no operations. Then at the end of the no-op operations, when it will find the malicious code, it will execute it and gain the access to the command line. And for this reason, we are just first locating the first line of where the variable a is stored in the memory. The variable a means we are using a into 256 times, so the variable a will be stored 256 times, and the first variable a is stored at this position. So we are just taking note of this space into the memory. Now whatever we want to do is that we want to make the buffer overflow by finding what at what position the buffer overflows. Let us just first quit it. Let's quit debugging since we have pointed breakpoint there. Yes, again we enter into the debugging mode, then we run Python command using double quotation print. We'll have to print a into 256 times, 260 times, sorry, since it is executed normally, so there is no buffer overflow. then let us try 264 times. It exists normally. Let us try 268 times. Now whatever happening is here, we see that 0x70 to 0x0. Which means although there is a signal seek kill illegal instruction, which means that we have just overwritten the previous frame pointer, but we haven't overwritten the return address. We have just hit the previous frame pointer with A, but the return address still remains. So we'll have to overflow and write the return address. Now if we just use the 272 age retain 272, we will see the hexadecimal value 0x41. That means the return address is also overwritten. Let's see, the return address is also overwritten. You can check this also by using x to a into 268 times and plus 4 byte b 4 times and 4 byte b, and then if we run the command, it will be seen that 0x42. That means b is taking the place for the return address. Now whatever we want to do is that we want to set this return address to that whatever we took care of, that means this position. So how can we do this? And we want to run a malicious program. So this can be done by whatever we want to do. A is 220 times, and then A, sorry, we not A. We want to just ensure no op operations. No op means the program will not execute the instruction, however it will move into the next instruction, and this can be done by /x90, which is the symbol for no op operations. Thus 220 times means since the return address is overwritten after 268, 268 means the last 4 byte is for the return address, and the malicious code we want to enter is about 46 byte. So if we minus 268 minus 48, 222, and we want to enter the malicious code. First let us write the return address. Taking the return address, we just write the return address. That means the start point of the whatever the variables are stored, and then we want to execute a malicious program, and this start return address will indicate the first position of the no op operations, where we are using the in the previously is 268 times there, and here it is 220 times no op operations. So this address indicates the first position of the no op operations. Then there will be malicious code, which is what is the malicious code? This is the malicious shell code. Will come into explanation after a few seconds. Let us just write the malicious code. We have written down the malicious code and the return address and the no op operations. That means first the no op operation is filling the 220 times, and then the malicious code. That means that we have written the stack previous frame pointer, and the last in the previous command we used BBB, and we are here it was shown that for 44, that means return address was shown, and in that position we are just showing the first position of the no op operations. Now if we just hit enter, we are getting command to the shell bin bash. So you can see that we have successfully run a buffer overflow attack to get command access into the shell command, and whatever that malicious code meant is that we can see it from here. uh, Malicious code is executing a command exec v with parameters name gem is beansh, and the name command with beansh and whatever variables is that will be 0, and the null command. And whatever it is doing is that it is first the system calls are executed from the lower end to the upper, and whatever it is doing is first calling the system to find is that we are making the CPU. We interrupt the CPU and say that please look at the system call table at position system call table, and we tell it to look at position 11 where %al means it's a part of the register EAX. You can see it here. It is part of the system called EAX, register EAX, and whenever the system calls the exec command, that means the 80 commands tells it to look into the system call table, and at position 11 it is the exec call. It takes 3 parameters, and 3 parameters are into the register, should be in the register EBX, ECX, or EDX. And sorry, let's return. Now here we see that whatever we are doing is that it's making system call, as I said earlier, system call to look at the system call table 11, that means exec v, and the it will take 3 parameters bean sh, which is set here, bean sh, and then it's taking argument v. Argument v will point the address. That means here we see that move EASP to EABX. That means it is taking the address ESP to EBX, return address of that position. So we get that EBX equals to these two characters, very 4 bytes and 4 bytes, which is saying that /bin/sh. Then argument v. In the argument v, there will be 2 parameters, beansh and 0, which is done by that is ECX. That is done by taking the address after putting 0 here. That means in the first we see that EAX equals to 0, XOR UX equals to 0. If there is /bin/sh, then here is 0, and push 0 EAX means here it will be 0, and push EBX. EBX means this address means this /bin/sh. So then move pointer /% ESP means that current pointer ESP to ECX. For better understanding, you can see it here. First, this parameter is set to 0. There is beansh address. That ESP, that means ECX is indicating this address and 0. So variable ECX is address and 0, 2 parameters. And in case of EBX, that means here there is bean and sh /bin/sh, so it's taking 1 parameter, and EDX/CDQ is 0, set to 0, with side effect of /x19. So this is the whole malicious code, which is telling that to execute in the command line the 2 variables, so that we can get access to the shell command, which is here. So the whole system is done to exploit the buffer overflow attack to get access to the main memory.